All right, everyone, let's get started. For people on YouTube, I hope the video is viewable. Let me know in the chat if it has some issues. Okay, so today's topic is neural language models. So if you recall, last time we discussed n-gram language models, which we estimated from a large data set of text by simply counting and then dividing. So today we're going to look at a more complicated class of models that performs better but also is not as simple to implement. So before we get started, some stuff from last time. So your homework zeros they're due on Friday. After this lecture, you should have more than enough knowledge to complete the second part of the homework. If you haven't started, please do start. There is some non-significant writing component involved in the last problem, which will hopefully also give you a good background for your final project proposal. Regarding final projects, again, your groups should be formed by February 7th and submitted to the Google form. If you don't fill out that form, we will randomly assign you to a group. We will try to put everyone in contact with their group members by February 8th. Then you can organize amongst yourselves and get started on the proposal. So we had a bunch of requests for people to get added to Gradescope or Piazza. Everyone should be on it that's currently enrolled for the class. If you're still not for some reason, email the instructor's account. All right, anyone have any non-course topic related questions? Great. So let's briefly review what we discussed in the previous class. Remember, we were talking about language modeling, and our goal here was to compute the probability of some input sentence, which we were also able to factorize into the product of these conditional token level probabilities, right? So any model that computes one of these probabilities we called a language model. We observed that we can easily get language models by applying the Markov assumption to limit the size of the prefixes that we consider. When we do this, we can get things like bigram models, which condition the prediction on the next word on only the previous word and nothing else in the context. So, of course, these models are limited. We talked about many of their limitations, and we would like to get models that can learn richer features from longer prefixes and use that information to condition their prediction to the next word. So this was the equation we saw from last time, and here we'll look at a different example. So if I want to predict the word that comes immediately after the prefix students open there, how I would do that is I would take from some huge corpus, I would count up all occurrences of this prefix, students open there, and then I would look at the count of every word that appeared after that prefix, right? And then I would normalize by the count of the prefix to get a probability distribution. Some words that might have high counts after this prefix could be things like books or laptops or so on. These words you might expect to get a high probability after doing the normalization. Right? So we talked briefly at the end about the sparsity issue, right? So what happens if students opened their word, W sub j, never occurred in the data at all? Then this WJ has no probability under our language model, even though it might be perfectly acceptable and we just didn't observe it in our training data set. So what we might want to do to avoid the problems of just zero probability on our test set whenever we encounter this prefix in this word is to apply smoothing, right? So in smoothing, we're essentially going to steal some of the observed probability mass and put it onto the unobserved words that we never observed in our training data set. We also talked about another problem with n-gram language models, which was the storage cost, right? These are exponential in the vocabulary size of the model. So it's really not feasible to scale this up to like a 100-gram model. You would need to keep track of, a huge number of counts, not to mention all the sparsity problems associated with that. So we would like to have a language model that maybe doesn't have these issues with zero count words, also doesn't have these enormous storage costs, and also would work better when we have longer prefixes and doesn't resort to chopping off the prefix after the last like k words. So these are some of the things in mind when we shift gears to another class of models. And an even bigger issue, setting all of those things aside, is that in an n-gram model, we treat all of the prefixes and all of the words as if they're completely independent of each other. They mean completely different things. They're all equally similar and dissimilar to each other, which we know in practice is just not true, right? So students open their blank, scholars open their blank, undergraduates open their blank. Like all of these things are very similar, right? These prefixes mean similar things, but when we're counting up in our count table, which words come after students open there, that has no influence on the same counts of what words came after undergraduates open there, right? We're not sharing any information between these semantically related prefixes, and we know that that would be very valuable, right? If I had something like pupils open there, pupil is probably a much rarer word than students, and so it would really benefit from sharing information from a prefix that had students instead of pupils. All right, so the reason why we're not sharing any information in n-gram models is because they rely on what's known as the bag of words assumption, in which every word or every n-gram in our vocabulary is represented as a one-hot vector. So we call a vector like this. So let's just say we're looking at words for now and set aside n-grams. Let's say we have a vocabulary, I hate, love, the movie, film. So we have 6 words in our vocabulary. A one-hot vector is a vector in which all of the elements but 1 are 0, and the only single non-zero element is 1. So you can see here that the word movie is represented by this vector, 0, 0, 0, 1, 0, where this 1 corresponds to the index of this word in the vocabulary. So every time I see movie, I'm going to have associated with this vector. Every time I see film, I'm going to associate it with this vector, where the 1 is now in the last position of the vector. Similarly, when we're estimating our n-gram models, we are essentially treating every unique prefix as a different item in our vocabulary, right? So we have a separate row in our table for each of these, and they are completely distinct from each other. Okay, so what might be some issues of representing a word or an n-gram in this way?
In a shared space, we don't know multiple kinds of values, probably relevant.
Right, so I have no way of knowing that movie and film are semantically similar to each other, or almost synonymous, right? If I look at any similarity metric computed between these two words, it's just all words are going to have the same exact score, right? So all words in the vocabulary here are equally similar or equally dissimilar, right? If you look at the dot product of these vectors, of any two vectors in this one hot representation space, it's always going to be 0. All of the vectors are orthogonal to each other. So every time I do something with movie, I never get to share any information with anything related to film. So ideally, what we want is a representation space in which words that are similar to each other, whether that be syntactically or semantically, or phrases or sentences, can all be close to each other in this vector space and farther away from words or phrases to which they're dissimilar, right? So we might want our vector space to be more meaningful than this one hot space where everything is orthogonal. All right, so this is kind of where the neural networks come in learning a representation space where we can make these kinds of distinctions, like these two words are semantically similar to each other, these two words are different, and so on. So instead of just counting up all the occurrences of students open there and dividing it by, in our count and divide framework, in a neural language model, we're going to pass this prefix, students open there, through what's called a neural network, and we're going to get a low-dimensional, real-valued vector representation of this prefix. So this is different than our one-hot vector. It's smaller dimensionality, and all of the values are not binary 0 or 1, they're real values. So we'll see some examples of this later. And we're going to use this vector representation to predict the identity of the next word. So we're not going to rely on simple like co-occurrence statistics to get us the probability of the next word. We are actually going to convert this into a classification problem. So given a representation of our prefix, students open there, we are asking a model to predict a distribution over the next word. And this is a learning problem, and we'll see how to tackle this in the next, in this lecture and the next one. So specifically in this lecture, we'll be looking at the forward pass. So this means, let's say we have all of the parameters of our neural network already, and I'll explain what parameters means in a bit. How do we go about getting from a prefix, like students open there, to a distribution over the vocabulary telling us what the next word is? So for those of you who are already familiar with neural networks, this will probably be very basic, but for others of you, this could be completely new, and hopefully it'll give you some idea of what to self-study in your free time if you are confused about any of these concepts. So next lecture, we'll look at something a little more complicated, which is how do we actually train our neural network to make better predictions of what the next word is. So this will involve the backpropagation algorithm, gradient descent, and so on. Again, all things that you've probably seen if you've taken a neural networks class or even a machine learning class before. But we will look at it specifically in the context of language models. All right. Are dimensions interpretable for prefix representation? That's a good question. So in general, if you're using a neural network model, the answer is no. You cannot actually interpret any single dimension of this vector and say, oh, this corresponds to like the part of speech of the word, or this corresponds to how many words are in the phrase, or something like that. We will talk at length about how to interpret or how to get some insights from these vectors, but that'll be well into the semester. We will talk about things like probe networks, which are used to kind of extract those insights from a representation. Okay, any questions on this high-level overview? So if you are new to all of this stuff, the pace might be quite fast, and I would highly recommend you go through the material, make sure you understand all of the equations and numbers and so on, because it's only going to get faster from here until we get to the transformer model. So there's a lot of different stuff, like basic building blocks that you need to understand in order to understand the current state-of-the-art architecture in NLP, the transformer. So we're trying to get there pretty quickly so we can talk about applications and so on. So the next 2 weeks might be a good time to budget some time for studying up on some of the stuff that you're confused about. And again, feel free to attend any of our office hours to if you have any conceptual questions or whatever. Okay, so let's get started with these neural networks. Again, we're talking about the forward propagation phase. And we'll, in this lecture, assume that words are the basic building blocks for our network. They form the input of our network, a sequence of words. In general, as we'll see later in the semester, this isn't always true. We might have as input a sequence of subwords or a sequence of characters or a sequence of bytes or something like that. But for the sake of explanation, let's just assume that we're talking about words today. Just know that it's a little more flexible than that. So if I have a sequence, like students opened there, I'm going to represent every word type in my vocabulary with a real valued low dimensional vector, which is also called an embedding. So I have a word embedding associated with every word type in my vocabulary. That means every unique word in the vocabulary, right? Not every occurrence of that word. So, for example, this word king, I might represent with this 4-dimensional vector, 0.23, 1.3, negative 0.3, so on. You can see that this is not a one-hot vector, right? And all of the dimensions here are real valued. This is also a 4-dimensional vector. It is not of the size of the vocabulary. So it's a dense, real valued vector. And our hope is to learn the values in here through the backpropagation and gradient descent process that we'll talk about in the next lecture. But for now, just assume we already have some process that learns it, and we have at some point some numbers associated with this king vector. So there was a lot of work before neural language models actually became, like the fundamental model behind NLP. There's a lot of work on learning word embeddings that have meaningful vector spaces where, for example, you can see in this middle picture, the past tense forms of verbs seem to lie in a interpretable direction and distance away from another form of the verb, right? So walking and walk, swimming and swim. Similarly, you can see a country and capital. They have these relationships. So basically, if you know that you want to find the capital of a country in the vector space, you can always move in this direction in the vector space and find it. So again, these are relationships that you would never be able to uncover in a one-hot representation space because they simply don't exist. Everything is equally similar. But here, now that you have this added flexibility, you can have a vector space that represents many more interesting concepts. Okay, but assume that we've represented all of the word types in our vocabulary with this embedding, with each with a separate embedding. Now, the goal of a neural network is to do the process of composition, which is we want to take a sequence of word embeddings and output a single vector that represents the meaning of that sequence. So here, students open there. I have 3 separate word embeddings. So those are these little rectangle things. So I have 3 separate word embeddings, each for one of the word types in the sequence. And now I'm going to apply a neural network to the sequence of 3 embeddings, and it's going to spit out a single vector. Does that make sense? Okay, so I can use one of these neural networks to compose phrases, sentences, and even documents into one vector or a small set of vectors or something like that. In essence, all of the stuff we're going to talk about with neural language modeling and so on consists of essentially squashing an input sequence of embeddings into another vector, either a single vector or a sequence, which is then used to solve some task. How do we decide on the dimensions vector size? Does it give a better performance with longer vectors? So the size of these word embeddings here, for illustration, I just showed a 4-dimensional embedding. In general, this is considered a hyperparameter of our network, which means that it's something that we as the designers of these models decide on before actually training the network. And generally, we are going to try multiple values of the hyperparameter and pick which one performs best on a held out data set to choose as our final model. So we'll go into that more later on in the maybe next week sometime. Okay, so let's say that I have a neural network and it takes as input these three embeddings. It outputs a single vector. And now I want to use this vector, now that I have a representation of the full prefix, I want to use this vector to predict the next word, which is books in this example, right? So for this class, we're basically going to just work our way backwards. We're going to start with the second step of, given a representation of the prefix, how do we actually go from that to a prediction, so essentially a distribution over the entire vocabulary of what the next word is. And after we've done that, then we'll get back to this first step of how do we actually go from 3 embeddings to 1 embedding using a neural network. Okay, so the most important concept for the second part of actually predicting the next word given the prefix representation is called a softmax layer. At a very high level, what this does is it takes an input vector and it converts it into a probability distribution over your desired output space. So here in this task, our output space is the vocabulary, right? All of the word types in the vocabulary. I want to know which of these word types has the highest probability to occur after this prefix. So this might look something like this. Again, at a high level, I have this vector from before that I got from this process of composition. And now I'm applying the softmax layer to get a probability distribution over the entire vocabulary. So here, the vocabulary is shown ordered alphabetically. In practice, it doesn't matter whatever order it is. But you can see that books here has a high probability. Laptops has a high probability. Some other words that aren't shown have low probabilities, and so on. So this is what we desire, right? And given this, we can generate text as well, right? So if you remember from the previous lecture, one thing I can do is always pick the highest probability word to generate next, or I could sample from this distribution using the probabilities as sampling weights, or I could do many other things. Yeah.
Does the model build up a vocabulary as it sees new words, or does it kind of receive new vocabulary?
Yeah, that's a great question. So the question is, does the model build up the vocabulary as it sees new words? Like, does it add them to its vocabulary? Or is it all fixed beforehand? And usually the answer is it's fixed beforehand. So you compute your vocabulary over some huge data set. This generally is not very computationally intensive, right? You can imagine, using a method like what we have in homework 0, I just split all the words on white space and then consider and form a vocabulary out of those. We will look at more complicated algorithms to produce the vocabulary that do something a little smarter than that. But in general, we are not adding new words to our vocabulary while the model is training. You can see why you might want to do that, right? What if you train your model on data before 2018, and then all these things that are new entities or events or words even that are created that aren't part of your vocabulary, you don't really know how to deal with them. On the other hand, we have models that are at the character level or the subword level, which can kind of handle some of that. So anyway, it's a great question. We'll talk about it more later on in the semester. Other questions? Okay, let's move on then. So this is the process that we're trying to explain right now. How do we get this vocabulary? How do we get this distribution, which corresponds to what we were talking about in the last class, right? This conditional probability of the next word here, W sub I, given now not the count, or not the we're not counting anymore. We now have this vector that represents students open there. and we want to get our conditional probability distribution from this vector. Okay, so I think it's best to explain this through a simple example. So let's say that our output vocabulary has only 4 words, because that's all I could fit on this slide. So we have books, houses, lamps, and stamps. So our model is going to predict one of these 4 words that follows the prefix students open there. So we want to get something that looks like this. A probability distribution, a 4-dimensional probability distribution. Note that our vocabulary has 4 types in it. Each dimension is going to correspond to one of the different words in our vocabulary. And so this means we have a 60% probability of predicting books, 0.1% that lamps is the next word, 0.1 that stamps, and so on. I mean, this is probably not the desired probability distribution, but we want something that looks like this, right? So how do we actually do this? So let's actually get some numbers into our example to make it more clear. So here, this vector at the bottom represents our prefix, right? So let's say it's a 3-dimensional real-valued vector. We got it as the output of our neural network, which is doing this composition process. And it has these values, -2.3, 0.9, and 5.4. Now, our SoftMax layer will have to first accomplish this task of getting this 3-dimensional vector into a 4-dimensional vector, because note that our desired distribution is 4-dimensional, right? Each dimension corresponds to a word type in our vocabulary, but we're starting out with a 3-dimensional vector here. So how do we do this projection to get from a 3D to a 4D vector? We can do this with a simple matrix vector product. So in neural network terminology, you'll often see this called like a linear layer or a feed-forward layer, fully connected layer, all of these different terms. But it's essentially just a matrix vector product. So we have a matrix W, and you can see that it is a 4x3 dimensional matrix. So if we compute this product Wx, we're now going to get a 4-dimensional vector as our output, right? So, but let's take a look at what actually that even means. Like, what is this matrix vector product actually doing? So when we're doing this projection from 3D to 4D, we're using this matrix W, and we can think about each dimension of X. Remember, X here is our prefix representation of students open there. We can think of each dimension as corresponding to some feature of the prefix. So, I mean, intuitively, you might say that, you know, the first dimension could correspond to some sort of syntactic information, or the second dimension to some semantic information. In practice, this is not true. You cannot make these clean assumptions that each feature corresponds to something interpretable to a human. But this is a good way to think about it just intuitively. Like, these are features that the model thinks are important for this prediction of what is the next word. We may not understand what these are, but intuitively, you can think about each of them as a feature. And then every row of this weight matrix W contains feature weights for a corresponding word in the vocabulary, right? So we have 4 words in our vocabulary. So this first row is the feature weights for books. The second row is the feature weights for houses. Third row for lamps. Fourth row for stamps. And so the prediction of each of these words is going to be dependent on some weighted combination of the features in the input. And the weights are defined by this matrix here. So let's see what this actually means when we take the matrix vector product. And again, we cannot easily interpret these features. So if you think that, you know, -2.3 somehow corresponds to like the length of the prefix or something, you're wrong. You can't really interpret it like that. Okay, so when we take this matrix vector product, Wx, we get a 4-dimensional vector now, right? So if you're not sure why we get a 4-dimensional vector, or you're rusty on your matrix vector products or whatever, you should quickly do some sort of linear algebra refresher just to make sure you understand what's going on. Because in all subsequent classes, we'll be talking about dealing with matrices and vectors and sometimes even tensors and so on. So it's good to be at least somewhat comfortable with these things. Okay, so we take this matrix vector product, Wx, and let's look at how we actually get these things, just as a refresher. So this first number here, 1.8, is associated with the first word in our vocabulary, books. So we take the feature weights for books, and we multiply them. So we essentially take the dot product of these feature weights with our input prefix representation. So that means we do 1.2 times, negative 2.3, and we add that to minus 0.3 times 0.9, we add that to 0.9 times 5.4, and eventually we get 1.8, right? So we can do this now for every other word in our vocabulary. So we had, books, houses, lamps, stamps. Here, that we have the values for books, houses, lamps, and stamps. So now we have some numbers. We have a 4-dimensional vector. So what else might we need to do here to get a probability distribution? This obviously is not one, right?
You could apply the SoftMax function to your length-4 vector.
So what would that accomplish?
That would make sure all the values sum to 1. It would turn your vector into the probability distribution.
Right. So we want some function that transforms this sequence of, like completely unconstrained sequence of numbers to a vector where all of the values sum to 1 and are non-zero, right? And so a function that accomplishes this is called the softmax function, as you said. So basically, you take your output vector here, this matrix vector product, you exponentiate like each dimension of this vector, and then you normalize by the sum of the exponentiated values. So here in this equation, x is a vector, so you can think about it as it's any vector really, but we would like to apply it to the output of this matrix vector product. X sub j is a dimension, one particular dimension of this vector x, and each dimension of the softmax output, so the softmax x, represents the probability of the class associated with that dimension j. And so here the classes are word types in our vocabulary, right? So if we take this matrix vector product Wx, we get these numbers. I guess they're different than here, so I messed that up, but whatever. It's still not a probability distribution. And if I apply the softmax to this vector, I get a well-formed probability distribution. So at this point, you might be wondering, why do I use this function? Why can't I just do some other form of normalization? One reason for, so there's many reasons. One reason for this is that we generally like to interpret these outputs here, the unnormalized scores, as log probabilities, unnormalized log probabilities. So this will make more sense after we go through the next lecture. But exponentiating them and then normalizing them makes it like we're operating on the raw probabilities, which is what we are getting as output of our softmax layer. So that's one intuition why, although people have proposed many other normalization methods that are, can replace the softmax. In general, the softmax also has a nice derivative when you're working with the cross entropy loss, which we'll also discuss next lecture. Okay, so we will be using this function over and over again this semester, not just for getting output class probabilities like here, but also in things like attention mechanisms. So make sure you understand it. It's very easy to implement, and there's also many implementations of it already in libraries like PyTorch and so on. Even in your homework, you'll have to play around with this. So make sure to understand it. All right, we have a question. Each row in W corresponds to a word embedding. That is actually an interesting question. Yeah, you can, I don't want to be too misleading here, but oftentimes people will do what's called tying their word embeddings to their softmax layer, because if you'll note, this matrix W is actually the same dimensionality as a matrix holding your word embeddings, right? The dimensionality of this is generally one of the dimensions is the size of the vocabulary, the other one is the dimensionality of your model, which could be the same dimensionality as your embedding matrix. So that might be too complex for now, but yes, you can interpret these things as embeddings, although in general, we use a separate matrix W for the word embeddings and a separate matrix for the softmax layer, even if they are of the same size. Does any function which brings things between 0 and 1 consider to give us a probability distribution? Yeah, so there are certain properties of the softmax function that make it better than other functions, but there's also other alternatives like the spherical softmax or whatever. You can take a look if you're interested in those, but yeah, it gives us nice probabilistic interpretations of what we're doing, especially paired with the loss function that we will talk about in the next class. So these were good questions. I hope you will understand those answers more as we get into the nuts and bolts of these models later on. Yes?
Does the model actually is the model able to handle context in this case? Suppose we are talking about math from a financial point of view and from a water point of view. So if we train the model on, say, examples which is talking about the financial math, and if we treat this matrix which is at the end of the model as the vector embeddings, as the embeddings of all the words which are there in the vocabulary.
Yeah, so I guess your question is, essentially, we have a separate row in this matrix or a separate vector, a word embedding for each word type in our vocabulary, but some of these word types can have multiple senses, right? Like bank can be a financial institution, it can be a verb, it can be a river bank, right? It can be many different things. And so why are we using just a single vector to represent all of these different meanings? Should we use different vector? Is that what your question is? Yeah, but I guess the neural network part of this whole framework, so over here, is tasked with coming up with a good prefix representation such that in the softmax layer, any of these possible meanings of bank can be considered as, like, if bank is appropriate in any of its senses, it could be, highly probable given this prefix representation. And in practice, that's generally true, although people have experimented with, adding different embeddings for every sense of the word. It's just hard to know for many words how many senses should they have, or so on. This is another thing that is less of an issue when you look at alternate tokenizations. So at a character level, right, this is no longer an issue, right, because you're predicting one character at a time. You have to predict a sequence of characters for there to be any word sense issues. So yeah, it's a good question.
So it could be possible that the matrix which we have at the end, it has features, one of which can actually get the river bank probability go up and the other feature can get the
yeah. I mean, the neural network part of this, these language models is usually huge and very, very nonlinear and complicated, so it can learn lots of these different properties. Yeah. Okay, so the output dimension has to be the size of the vocabulary. Yes, for this final softmax layer, the output dimensionality is always the size of the vocabulary. All right, any other questions? That's a great question. So how do these models deal with the variable size of the input? Maybe that is a nice segue into the next part. Yeah, we'll cover that right now. Thanks. Okay, so just to review whatever we've learned in this part of the lecture, we have some process which involves a neural network for coming up with a d-dimensional, some low dimensional vector representation of our prefix. And given that d-dimensional vector, we first are going to project it to a vector of size v, where v is the size of the vocabulary, the number of word types in the vocabulary. And we're going to do this with a matrix vector product, right? A linear layer or a feed-forward layer, as we saw in the slides. And once we have our v-dimensional vector, we're going to apply the SoftMax function to obtain a probability distribution of what the next word is. Was that generally clear? All right, so now going back to your question, how do we actually get this vector representation x of the prefix? So we look at two, and also Alan's question here, we look at two methods in this lecture of how to do this. But really, this is one of the core problems in NLP. People devise many different model architectures for the task of taking some variable length input sequence and coming up with a vector representation for it. So let's take a look at two different approaches to compute this prefix representation x over here. In general, this is a process called composition. So any function that takes a sequence of word embeddings and outputs a single vector we'll call a composition function. There are many different types of composition functions that we can use. So in your homework, we ask you about element-wise functions, which you can say, if I have, these word embeddings here, students open there, I can just sum them all up element-wise. So sum the first dimension of each of these vectors, the second dimension, the third dimension. I get a new three-dimensional vector that has information from all of these word embeddings, right? This, however, isn't a great way of doing things. Why is that? It could have.
It should have different weightage. All the words should have the similar weight.
So I didn't quite get that.
No, I think every word that embedded all the vectors have a different weight. Like we can assign a particular weight to a particular word.
Uh-huh.
And that we can get a better probability.
Yeah.
Summing up doesn't capture the syntax of the sentence, because even if you interchange the words, you get the same.
Yeah, exactly. So if I'm doing this element-wise function like adding or averaging, the representation for students open there is identical to the representation for opened their students, which is identical to their opened students, and so on. All of these different reorderings, which completely eliminates the syntactic information or the information about the word order and so on. You can see how this is an even bigger issue when we have longer and longer pieces of text, right? That said, this can still be a very useful composition function if the task you care about might not be very sensitive to the order of words, but rather the identity of the words in the text. However, that's not interesting to learn about. So there are other approaches. So one is concatenation. So I could form a representation of this prefix by simply concatenating these three-dimensional vectors to form one 9-dimensional vector. What could be an issue with this approach? So here I'm considering the word order, right? Because students open there is going to form a different vector when I concatenate than open their students.
As the sentence goes long, the dimension will be changed 3 times.
Yeah, that's right. So if I apply this concatenation operation, if I have a 4-word prefix, I'm now going to have a 12-dimensional vector. And if I have a 5-word, I'm going to have a 15-dimensional vector. And I don't know how to deal with that after, if I want to get a softmax layer, right? Because I need the input to be in a specific size. So yeah, that's one thing. So then there are neural network architectures that we could try, feed-forward neural networks using concatenation or element-wise functions, convolutional neural networks, recurrent neural networks, transformers, there are many others, but in this class, we will talk about feed-forward neural networks using fixed window concatenation, and we'll also talk about recurrent neural networks. Our goal in the next couple weeks is to build our way up to transformers, which will form the focus of the rest of the class. Sorry, the rest of the semester. Okay, so let's take a look at concatenation in a little more detail because it's very easy to understand, but as you mentioned, it has a severe limitation. So we can take a look at a neural language model that has a similar property to n-gram models in that it applies this Markov assumption, so it discards words that are outside of some n token long context. So here, if we have the prefix, as the proctor started the clock, the students opened their blank, maybe we decide that we will only ever consider the last 4 words as part of our prefix. So we'll discard all of these, but instead of doing the count and normalize approach as a normal like 5-gram model would, here we're now going to represent this truncated prefix with a vector using a neural network. So how do we do this? We have our words here, the students opened there, and each of these is associated with a 4-dimensional word embedding in this example. Again, the word embedding dimensionality is a hyperparameter. It's something that we decide on prior to training these models. We're just showing a bunch of different examples here. So here, the word the is associated with 4-dimensional vector, students is associated with a 4-dimensional vector, and so on. And the first thing we do is concatenate these together. So now we've formed this 16-dimensional concatenated representation of the prefix. Now, one thing that might be familiar to you if you have studied neural networks is the concept of this hidden layer, right? Which is a linear layer, as we saw in the softmax layer, followed by a nonlinearity, an element-wise nonlinearity. So let's start with the linear layer part. Here, we take our 16-dimensional vector and we use it in a matrix vector product where the matrix W sub 1 is of size 12 by 16. So when we take this product W1x, we are left with a 12-dimensional vector instead. So note that here, we're still not considering the softmax output. This is part of our internal process to arrive at the representation of our prefix. So once we do this matrix vector product, we then apply this nonlinearity, which here is marked as f. There are many different functions that could be used as a nonlinearity in this process. What is most commonly used today is called the rectified linear unit, or ReLU, which basically just sets all negative elements in the vector to be 0. Other common choices are the TANH or sigmoid or whatever. There are many different variants of the ReLU that people use today. But yeah, someone familiar with neural networks maybe can explain why do we put a nonlinearity in our model? What are the benefits of doing this? Why don't I just say h equals w sub 1x and call it a day? Right, so I expect in this task of language modeling or in the task of coming up with, a representation of a phrase that the relationship between the input word embedding sequence and the output of the next word is highly nonlinear and might depend on many, many different complicated things. And if I use no nonlinearity at all, I may not be able to learn many of these relationships. So one commonly used strategy in neural networks is just to stack more and more layers on top of each other. So I could have h sub 2 equals w sub 2 h sub 3 equals w sub 4 h sub 2, and so on. I could just build more and more layers, put more and more weight matrices into this computation. If I don't have any nonlinearities in this process, then I can always come up with just a single transformation that essentially is equivalent to stacking all of these linear affine transformations together. I can't do that if I have a nonlinearity in the mix. So it also helps us efficiently use the concept of depth in a network to learn these more complicated functions. Okay, so I have multiplied this concatenation by a matrix. I've reduced its dimensionality. I've applied this nonlinearity. And now this red vector here, which is 12 dimensions, is going to form my representation of the prefix. So this contains, ideally, the meaning of the prefix. And now I'm going to feed it into my softmax layer. So I have a new weight matrix here, W sub 2. And I'm going to project this 12-dimensional vector into the size of the vocabulary, and then apply the SoftMax function as we saw. And now I have a distribution over the next word. So in this whole process, I have a couple of things that in the next class we'll talk about actually learning. So these are the parameters of the model, which refer to what, in the process of backpropagation and gradient descent, we are actually adjusting every time we see an example. So my goal is, if I see the students open there, I want this output probability distribution to have very high probability on books and laptops and very low probability on words that don't make sense at all in this context, right? So every time I see this phrase in my training data, I'm going to hopefully try and adjust the parameters of my model such that next time I see this, it's going to put higher probability on books and laptops and lower probability on other things. That's the goal of the learning process. So when I say that, what do I actually mean by adjusting? What is getting adjusted here? Well, there's several things that contribute to the computation of this probability distribution, right? There's W sub 2, which is a matrix of the weights of the input representation. There's W sub 1, which is another set of weights. There are these word embeddings, right? These input word embeddings that themselves are vectors that form the inputs to my network. All of these have parameters. They are parameters. They're just numbers that can be adjusted so that next time I get a higher probability of books. So our parameters in this network are, C sub I, all of the word embeddings, W sub 1, and W sub 2. X is not a parameter of my network. Why is that? Someone just raise their hand and tell me. Yes. X here is the concatenated sequence of word embeddings, right? So X is actually formed, it's like an intermediate variable, right? It's formed by manipulating the input word embeddings. It itself is not an external parameter that I've added to this network, right? On the other hand, W sub 1, it comes up here and it's directly used to manipulate X into yet another intermediate variable H. Right, so H is not a parameter of this network either. It's merely a byproduct of multiplying our parameter weight matrix W sub 1 with another intermediate representation. Do you have a question? Yes, so these word embeddings, C sub I's, are also learned during the training process of a neural language model. Oh, yeah, the question is there any reason why we picked 12 and 16? No, it's just for the sake of the example. In practice, the dimensions are usually much larger than this. They could be in the hundreds or thousands. Any other questions? I saw, yeah. Yeah, so you can think of it like we're starting with one hot vectors that get multiplied by the embedding matrix to determine the CIs. But intuitively, you can just say, for every word type in the vocabulary, I've associated a different vector, C sub I, where the I corresponds to the index of that word type in the vocabulary. And whenever I get a new prefix, I'm going to first do this lookup process where for every word in the input, I look up its vector representation. So here I found that the is this 4-dimensional vector in my embedding space. And yeah, then I will train my embeddings as well. In practice, these embeddings are stored in a matrix of size v by whatever the embedding dimensionality is, and we do the lookups from there. But yeah, we're not going to discuss that more in this class. What if the probabilities are almost equal or tied? I mean, that doesn't make a difference to us. There could be cases where there are many, equally probable outputs for a given word. We'll talk about during learning why our ground truth training signal never has equal probability words. The next question, putting aside computational limitations, could we land at the same results by feeding the vocabulary-sized one-hot representations of words as input as embeddings to the neural network? That's a good question. You probably could, but you can also conceive of this same setup as the lookup process requires feeding a one-hot. So basically taking a matrix vector product between the embedding matrix and a one-hot vector where the one corresponds to the word that you're interested in getting its embedding for. So anyway, that's maybe beyond this class. Feel free to come to my office hours or something to discuss it more. Dimensionality of W1 is determined from the start to support only specific length prefixes. Yes, that's right. So W sub 1 is dependent on the size, the dimensionality of this is dependent on the size of the window, so here 4 words, and the dimensionality of the word embeddings. Right here, they're 4-dimensional. Okay, would we use perplexity as a performance measure here? We would use it for evaluating the eventual trained language model, but here we haven't talked about training yet. But yes, for any language model, neural or n-gram or whatever, we are going to evaluate using perplexity. All right, so yeah.
Yeah, that's the fixed window is like a general name of some 5 games, 4 games. So they are almost the same.
Is the fixed window always the same? Is that the question?
No. I mean, the fixed window represents like 5 games, a set of some number of games.
A set of.
The model like we discussed.
Oh, the n-gram model.
Yeah.
Yeah, so this model here, actually we'll talk about the similarities to those n-gram models right now, but yeah, we are using a fixed window like 4 gram or 5 gram. Here the difference is that instead of just counting and dividing, we're going through this whole neural network process to represent that prefix instead.
So later we will discuss how to choose the size, right?
The size of the window?
Yeah, how to we don't know the size or the more better or some is.
Yeah, so actually later this model we are only discussing for sake of example. In a few slides we'll discuss the recurrent neural network, which doesn't have the limitation of the fixed window, so just wait for that. Let me just hold the questions for now. I want to get through the comparison to the n-gram model, just to be clear. So this model, the fixed window neural language model, does not have a sparsity problem, right? Because we're now dealing with these dense representations instead of one-hot representations. So if I see students open there and I see pupils open there, ideally those 2 vector representations would be in the same space, and I actually share information across both of them when I deal with this low-dimensional real-valued vector representations. Also here, my space storage constraints are determined by the, they're not determined by the length of they're not exponential in the vocabulary, right? So here I'm only storing a different vector for every word type in the vocabulary, and I'm doing this process of composition to get a representation for a phrase. Whereas in an n-gram model, I have to keep a separate count for every possible phrase, which makes it blow up in exponential in the vocabulary. Okay, but we still have some issues with this model, right? First of all, our fixed window still has this problem that we're ignoring all this important context. And as you said, if we enlarge our window, we're going to add more parameters. Our dimensionality becomes bigger. And so another problem, which is more subtle, is that we are essentially saying that this matrix W sub 1 needs to understand how to process each of these words with a separate weight matrix, and we don't share the information across different positions of the sequence. So like if the occurred in the first position of the window, or if it occurred in the second position of the window, it's being dealt with two completely separate blocks of this matrix. And ideally, we would want to be able to share information such that regardless of wherever in this prefix the word the occurred, it would have some, we would be able to share information between that position and previous positions. Ideally, the word the is being processed the same at every position. Okay, so let's get to the last part of this lecture, which is the recurrent neural networks. I see a lot of YouTube questions, which I will ignore till the end, just for sake of time. But this model solves some of the limitations that we had from before. So let's take a look at the same prefix. The students opened there. I have these 4 word embeddings. Now, instead of concatenating the 4 vectors together, I'm, in a recurrent neural network, going to treat this as a sequential problem. So I'm going to, much like humans read a text from left to right, my model is going to process this prefix from left to right as well. And this has a number of advantages, as we'll see in a bit. So we will start out with our hidden state here. This is h sub 0, where 0 corresponds to the time step that our network is at. So we have some random vector, it could be a vector of zeros, or some learned parameter associated with the very first time step of this network, which means before the model has seen any words of the prefix at all. So now the very first thing we're going to do is process the first word of this prefix. So we're going to take our previous hidden state and update it with information about the first word. So here, the first word is the, and we're going to form a new vector, h sub 1, by a function that is dependent on h sub 0, the previous hidden state, as well as the word embedding for the very first word in the sequence. So if you take a look at this equation here, this is the recurrent neural network update equation. So we have h, it's a superscript, I'll just say h sub t minus 1, which is the hidden state from the previous time step. We're applying one matrix vector product with this matrix w sub h to project this hidden state into some new space. And then we're applying another weight matrix here, w sub e multiplied by the word embedding, c sub t, at the current time step. And we're going to add these two outputs together and apply a nonlinearity. And now we get a new vector, h sub 1, which has information about the first word of the sentence, of the prefix. Now we're going to apply the same process with the same exact equation, but we're going to move one step in the further in our sequence. So now c sub t corresponds to the embedding for students. H sub t minus 1 is the previous hidden state, which has information about the word the. And I form a new hidden state, which now knows about the students. I can keep repeating this process until I get to the end of the sequence, at which point I can put a softmax layer over the final hidden state of my recurrent neural network. And this is h sub 4. It has information about the entire prefix, the students opened there, right? By way of this recurrent update mechanism. And now I use a different weight matrix here, w sub 2, to accomplish the softmax projection into the vocabulary space, and then I apply the softmax to get my distribution over the next word. So we will go through these equations in detail in future lectures. We'll also look at backprop in a simplified version of a recurrent neural network. But here for today, I just wanted to show the intuition behind how this model works and why this is conceptually better than one of these fixed window language models. So someone tell me, what is an advantage of this left to right process over the fixed window approach? Exactly. So that is maybe the biggest advantage, right? Is that we can now deal with variable length inputs, right? Because the update equation here does not depend on how many words are in the prefix. I'm using the same equation one step at a time. So if I had a prefix of 10 words or 3 words, it doesn't matter. I can still use this to compute a representation of the prefix. Whereas my fixed window language model, I can't do that, right? I always have to use one constant number of words in the prefix because my parameter sizes are dependent on the choice of that size. So that is one of the biggest advantages. And this computation at time step t, relatedly, can theoretically use information from way back in the sequence, right? In practice, RNNs are pretty limited in the effective context size. So if you give it a really long sequence, it probably won't be able to have some deep understanding of whatever content there is in that. But in theory, at least, it can handle arbitrarily long sequences. And again, going back to this weight sharing thing that I mentioned before, here, the same weights, right, W sub H and W sub E, are used at every time step of the sequence. So if the word the occurs at position 1 or position 3, it's going to get the same weights applied to it, right? In the fixed window language model, that's not the case. If the word the occurs here, it's being dealt with a completely separate block of this weight matrix. So if that doesn't make sense to you, you might want to draw out the computation that's happening here and move like the word the to different positions and see what weights in the weight matrix are actually used in the computation to produce the next hidden representation. So some disadvantages of this. The recurrent computation is slow, as you might imagine. Now, for every prefix, I have to go through n computations, where n is the length of the sequence. In the feed-forward case, the fixed window case, this really wasn't an issue because concatenation is very fast, and then I just have one computation on top. But here, a 10-word sequence is going to take longer to process than a 3-word sequence. And there's some practical issues with dealing with information from many steps back, which we'll talk about later on in the semester. Okay, so I have about 8 minutes for all of your questions. Let's do some YouTube questions first. Alan says, so the dimensionality of W1 is determined from the start to support only specific length prefixes? Yes, that is the case in the fixed window language model. Oh, I think I already answered that, my bad. Are we keeping the words the there as they are stop words, or in practice we remove them? Currently we do not do any removal of any information in the input. Previously people used to do stop word removal and stuff like that, but nowadays it's not generally done. Aren't we limited by the complexity of the word embeddings for such models to work? In modern models, the word embeddings do not form the majority of the parameters in the network. We actually have way more parameters at different layers of the model, and so no, we're not at all limited by the complexity of the word embeddings. This is not relevant for the class. Any questions from all of you here?
In the fixed window language model, if we select a maximum length and then just put some added brackets in the end, so we can have the standard variable length.
So the question is, in the fixed window language model, if we select some very large length and then just pad all of the prefixes to be of that length, can we get some of the advantages of like, can the model handle arbitrarily large context? In general, the problem with that is that you run into this weight sharing issue where, like, why should a word that occurs 1,000 tokens ago be processed differently than a word that occurred 800 tokens ago, right? So it's not as much of a context processing issue, like context size issue, as it is that this is just not an efficient way of producing representations of a lot of a long text, because you'll need to see a lot of instances of words in different locations to accurately train the parameters of that network. So a recurrent neural network for that kind of context size has a much smaller set of parameters that learn very quickly to generalize to many different kinds of words, which is why we use that kind of network. But that is a good question. There have been some papers, even some of my students have explored scaling up this kind of fixed window language model to much bigger window sizes and see how they perform against the state-of-the-art transformer language models. The TLDR is, the modern models are much better than this kind of thing. Other questions? For the, is the hidden state fixed for the recurrent neural net? Oh, the initial hidden state. Yeah, so this is something that depends on your implementation. It used to be common to just initialize this to all zeros. Some people initialize it as a random vector, which is trained. It usually doesn't impact the performance no matter what you do. Okay, oh, I see we have one more question. Does skip connections help with accessing information in shallow layers for RNNs? We will talk a little bit about variants of RNNs that help, that kind of increase the effective context size, but they're mostly memory-based models, and we won't talk too much about them because we'll switch over to transformers. But okay, for next time, you can be prepared to learn about backpropagation. We will do the entire lecture on the iPad instead of on the slides, so hopefully that'll be more helpful in digging into the computations as well. So see you on Monday, and make sure to submit your homeworks.